Welcome back. As you may have noticed, we have a new time, so not everyone is here yet, and I think we'll wait a couple moments for them to arrive. In the meantime, of those of you who are here, maybe if you want to share anything, if you're able to successfully assemble that U-joint assembly, feel free to share what you have. If you have any questions or problems, also feel free to share. We can look at that. If you can't hear me, if you have trouble hearing me, I am talking, so let me know and I'll figure out what's happening. So were you, the two of you who are here, were you able to successfully assemble the U-joint? Depending on where the class is, I might either spend some time on that or just go straight into the new stuff. Maybe type in the chat if you don't want to say something, but I'd like to hear some feedback.
So I have something. Can I show what I got right now?
Sure, feel free.
Screen share. It's called Air.
Yeah, so what do you have?
That's what I made.
Okay.
One on share. You see, that's the air engine thing.
Okay, is it one of the parts that were in the drawing PDF? Are you trying to show us something? Unfortunately, right now, I'm not meeting hosts, so.
Stuff no weight. Yeah, so that's my design right now. I'm doing stuff when I wait. What do you think? What do you think of my design?
Could you explain what you're going for?
What do you mean by that?
Or what do you want me to comment on, I guess, is the real question.
So, yeah.
Was that your, I guess, was that your submission for this?
Yeah, I was my submission for the
Okay, I see.
air engine thing.
Yeah, so I can talk about that in a moment. Seems like for now, we might just be getting 3 students, so it has been a bit of time, so I will just get started, and other students can, I guess, catch up as needed. We'll start off just going over the universal joint. I know I did show this last class, but it has been an extra long time because we did move the class. And thanks again for being flexible with that. So I do appreciate it. But your final assembly and the conclusion of this project, we're done with the U-joint assembly now. And it should look something like this. So if you have any questions, feel free to ask, but I've asked for questions and no one seems to really have any. So I assume that you all were able to manage to assemble this. Just to go through the mates, I start out with a fasten mate just to make sure my assembly has a sensible location with respect to the origin. So the origin is right there, as you can see. Then I have these two revolute mates, which allow the bearing cross to kind of spin with respect to these two clevises. And then lastly, we have these cylindrical mates, which again, you could theoretically have done this with revolute as well, since these don't actually slide in and out. But if you don't want to actually calculate the precise length that these rods need to be, then it's a bit convenient to use the cylindrical mate just so that you don't have to worry about how much of this length actually comes out. So in terms of that, nice work. Completed our first project of this class. And as you know, we're going straight into the next one. And you've already done part of it. That was the space plate. And I guess Christopher has shown us what he's tried. Remember that the main objective that we're kind of trying to train with this second project that we're doing is learning how to read from drawings. And kind of the whole exercise is you'll CAD things progressively more difficult, perhaps, just looking at these drawings. And so I guess before I didn't know what I was looking at, but now that I see this, I kind of see what you're doing. One thing I will point out is that these lines here, these kind of angled diagonal lines, they're not actually part lines, but rather it's just like an arrow that points to the diameter of this circle. So in your sketch, I believe you may have had these lines that you're trying to denote some kind of boundary, but in reality, this entire thing is just a square. So I do see that that may be perhaps a bit misleading, because last week I told you like solid lines are part boundaries, and now I'm telling you there are these solid lines that are not part boundaries. But for the most part, if you see like a number, that means a dimension, and then under that dimension you have like a line that goes to an arrow. Here it's hard to tell that it's an arrow because everything is so crammed in there, but this is just an arrow. It's not really part of the part. So with that knowledge, you're free to try to finish modeling this. Another thing to keep in mind is that this is like a 3D object. This is like a solid block or a plate with two holes in it. So you do want to finish up that extrusion. But other than that, I do see that you read the dimensions and you knew like how big to make things. And so hopefully with that experience now with the next homework, you'll be able to more confidently and accurately crank out these models. So if you have any specific questions about the homework, I'm happy to take them. If you have any like CAD issues or conceptual questions, now would be a good time to ask.
I don't have any problems right now, so yeah, okay.
You don't have any problems?
No, I don't.
Okay, great. Sorry, it's a bit of ambient noise around me as well. So hopefully in the future, I'll be able to walk back to somewhere more suitable. But right before this, I was doing something. Okay, so if no one else has any homeworks, we'll go into kind of the topic for today. And then after that, we'll go through like a demo style. We CAD stuff together, and then I'll introduce the homework, and that'll be the class. And the topic we're going to talk about is importing parts. So I believe we have not talked about this before, also in the previous class, but when it comes to CAD, it turns out that a lot of people use CAD, and a lot of people make these CAD models, even for parts that aren't custom designed. So when it comes to parts, when you're designing a system, you might design something that's custom. If you're trying to make a robot, you might design like a arm member that's the exact shape and size that you want. But they're also standard hardware, things like bolts and screws and nuts, bearings, things like that, things that you can buy at the hardware store. And those things follow standards. And what that means is that if you buy a certain type of bolt from one hardware store in Maryland, then you go across the country, you go to another hardware store in California. As long as you buy the same type of hardware, those things are going to fit together. And that's pretty important because You wouldn't want to make an assembly out of parts that can only be found in one region of Maryland, for example. So places where you can buy these like products, a lot of them will provide CAD models with the product. So it's not an advertisement for McMaster, but this is kind of one of the more famous catalogs where you're able to buy parts. I put a link in the chat. I guess it's a very short link, but if you go here, you can see that there is a selection of various objects, most of which are standard hardware. So for example, if I'm trying to design something that has bolts in it, the fact is I need to buy those bolts. And if I buy those bolts, then due to the fact that it is some kind of standard hardware, its geometry will be completely predetermined based on what I bought. So I'm just going in, you saw me click through some of these menus. Let's say I need a 1/4 inch by 20 threads per inch screw that has a length of, say, 1 inch long. That's this guy right here. And you can see here, I believe if I go to a specific product, seems like right now it's not letting me download the CAD. Okay, for some reason, unfortunately now I can't demonstrate this, but the idea is that a lot of the time in these parts catalogs, they'll provide a model for you. And the advantage of that is that, first of all, if you just download the model that's provided by the vendor, then you know that the CAD model that you're using to design your assembly is going to be correct because you're using the CAD model that the person who's selling you the thing has made. Another advantage is that you don't have to go through the trouble of making it yourself. So you can imagine that trying to model something like a screw or a bolt can be a bit more time consuming perhaps, and it's not really something that you would want to spend your time on. And so there's no need for you to try to model these things yourself. Just know that there's an option wherever you're buying stuff, more or less, it's going to be available. So there's an example here. I guess maybe there's a change with McMaster where you have to be logged in to download the CAD. But back in the day, you could just go here and download the CAD model, and you can import it into Onshape. And so that's the next thing I want to show you, which is how to import parts into Onshape. It seems like, unfortunately, I can't use McMaster, but I can probably use this thing. So McMaster was kind of a catalog for hardware. If you're trying to design a mechanical assembly, maybe trying to build a bicycle from scratch, right? You'd probably look there for CAD models. On the other hand, if you're more of a hobbyist, maybe you have your own 3D printer or you have access to a school's 3D printer and you just want to make cool things, maybe little simple machines out of plastic or like an action figure, things like that. There are also communities online for that where they also share CAD models and you're able to download these files. And Thingiverse is one example of that. I guess I'll put this link in the chat as well. But just by going to this like front page, you can see kind of a different type of environment. It's a different audience, but I can use it to demonstrate a similar idea, which is that of downloading and importing parts from wherever you find them to Onshape. So I guess this is a tape dispenser. I just picked it at random, but you can see on the right, there is that download link. You can save the file just like any other file. And from there, it looked to me like the file was zipped. So you can just unzip a file just like you usually do. And once you do, go in and you can see that they're STL files. So cool, I have these STL files. I don't really know what they look like or what they are. This one looks like it's all the parts of an assembly to make this tape dispenser that is pictured here. So how do I bring this into my own instance of Onshape? If you have some kind of 3D file, and there are numerous formats, most commonly you'll probably see .stl, .step, maybe parasolids, IGES, maybe even like a SolidWorks part. But the current one is an STL file. If you click on the plus sign at the bottom, just like you do for creating a part, you can see at the very bottom here, one of the options. Before we've done things like create part studio and create assembly, but we can also press import. And that brings up a file browser where you can navigate to wherever you saved that 3D file that you had. So this is the thing that I just downloaded off of Thingiverse. Let's see, maybe frame left might be interesting to look at. When you try to import it, it'll prompt you with this dialog box. Not too much here. You don't really need to click these unless you have reason to believe, like, for example, the second box, if you import like a bearing model probably has multiple parts. It's kind of its own assembly. So it gives you the option to just turn all of those into a single part, but I don't think it matters in this case. In general, you can probably just ignore it. Now you can see it shows that it's downloading. And after a few moments, I have my CAD file. So you can see I created a brand new document, and all I did was import this STL file, and now I have this model in my workspace. So it's kind of how you go about it. If you ever need to get something from online, this is how you would do it if you're using Onshape. And the main thing that I want you to learn is how to do that. So if you click the plus sign, you click import, and you just navigate to your file. Onshape will open it up for you. So we may use this later in the class, depending on, for example, if you run out of time with the Air Engine, I might just give you the model for the last parts that you didn't have time to CAD. And in that case, you would need to know how to download that part and then import it into your own Onshape document. But that's kind of how you would do it. So you can see I imported another one. Here it is. There you go. These are all created by that person on Thingiverse. Tetralite, I guess. I just clicked this one on random, but they are the ones who posted this to Thingiverse and made it available for other people to download. So if you have any questions about how to import things, let me know, but once you do it, you'll know how to do it. And it's a fairly straightforward process. So from there, we kind of have the flip side. We just demonstrated how you can take something from the outside world and bring it into your workspace. Now, what if you want to do the opposite? You create something and you want to share it with the world. For example, maybe you have a 3D printer, you have access to a 3D printer at your school. If you create something in Onshape, how are you going to get your model from your computer to the 3D printer? Or how are you going to get your model from your computer to someone else's computer? In case of Onshape, let's say that I want to export this lovely U-joint fork. Here we go. Let's say that I want to send this to my 3D printer. How do I get the file out? Pretty simple. If you go down to the tab for the Part Studio, you can right click on this tab. And when you do, this thing comes up at the very bottom, it says export. So you can try this for yourself as well. Maybe the last one, you didn't necessarily have to follow along, but this one, you probably have a part open anyway. So right click on the tab, click export. It brings up this dialog menu. You can give it a name, so my fork. And you can assign a format. So here, this is kind of what I mentioned earlier in terms of the fact that there are many different file formats. For example, you've probably seen a lot of file formats in other contexts, like .pdf for PDF files, .doc for Microsoft Word files, just like that. 3D models also have their own like file extension. So a very common one is .step. In general, I'd suggest that you probably use a step file, as it can be recognized by pretty much any CAD program. Some of these other ones may be more specific, like SolidWorks can probably just be opened by SolidWorks. But few of the other ones that I think are more general, Parasolids, I think you should be pretty good with those. IGES, I've seen, and .stl. This format is most commonly used for 3D printing. So if you have like a hobby 3D printer, you'll probably want to export as a STL file. And that's just a special way that the information is encoded when it's stored as a computer file. In terms of the other things, you'll have a few options, but they should be fairly self-explanatory, or if you're in a position where you need to know about them, there'll probably be someone who will tell you what to do, like if you're trying to run a 3D printer. So with all that said, you can just click OK in this dialog, and that'll prompt you to download a file, which you can do just like any other file that you use. That just saved that file into my own like file space. It's my fork. And so for example, I could like send this to someone else. I can put this on a flash drive and move it over to my printer if I had one. So there you go. Now you kind of have escaped the shell of Onshape. You have the power to move things out of Onshape and bring things into Onshape. If there are any questions, feel free to ask. But otherwise, we'll move into continuing our second project, which is this engine. So here's a photograph of the thing that we're going to be modeling. The other instructor for this class, when it was first created, his name is Jack. Maybe you've met him, maybe not. I think he teaches CAD computer classes for this program, but he created this engine in like a shop class in high school, and it's basically what we're going to be modeling. Perhaps slightly simpler because we don't have to worry about things like the counter bore like you saw on the base plate. That's purely there for physical purposes, for assembly, in terms of a 3D model where we won't have these fasteners. We don't have to worry about that, but this is kind of what it looks like. And our goal today is to model, try our best to model 2 more parts in class. So the first of these is going to be cylinder, and the second will be the crank wheel. So I'll give you a moment to appreciate this drawing. If you want to see it bigger on the Google Classroom, you can open up that document and look at it for yourself. But take a look at this drawing and tell me what shapes you see. Classic questions that we always ask ourselves. What shapes do you see? What features can we use? So describe this object to me. And I know it can be hard with looking at these like orthographic drawing views, but try your best. Nothing bad will happen if you say something wrong. Let's start simple. What shapes do you see? Let's see, Christopher. Hopefully you know your shapes. Can you tell me one of the shapes that you see on this drawing?
A rectangle.
Okay, so there are several rectangles, and we see they're drawn in these solid lines, which means they're part boundaries. So there's going to be some rectangles involved. Any other shapes? For example, can someone tell me what's going on in the middle of this rectangle? What is happening here where I have this dashed line with kind of a, maybe like a tower shape here? Jason, can you tell me what you think is going on in the middle of this rectangle? You can see it here too.
There's a hole in it.
Could you say that again?
There's a hole in it.
Yeah, there's a hole in it. And what's the shape of that hole? Just generally.
A cylinder.
Yeah, it's a cylinder. Nice. So I'm glad you remember how to read these drawings. This one's a bit more complicated than the one you did before, but the main ideas are still the same. We have a rectangular block, and we're looking here at the front, the side, and the top. When you look down from the top, you can see there's this circular hole in the middle. And when you look at it from the front and the side, you can kind of see this long channel. And that kind of tells you that you have this cylindrical hole, and at the tip, it kind of tapers off into a cone. For the outside geometry, we know it's a rectangular prism. Like from the front, side, and top, it's all rectangles. And from the side view, we kind of see these two additional channels. And from the front view, we see these circles. So that tells us there are two more holes located there. So great. In terms of the geometry, hopefully you can picture what's happening. Like you have a rectangular solid block, and in there you have one big hole that kind of goes through the long way. And then you have these two smaller holes that kind of come in from the side. So we will try to make that. I want you to open up the document where you created your base plate for the homework. Let's see. I'll just create a new one because I have so many files floating around. But we're going to start off just by CADing this rectangle. And hopefully you all have a good idea of where to start. You create your sketch, you draw a rectangle, and we're going to start to use our drawings. So I drew my first rectangle. The immediate question I have is, how big is this thing? So I go back to the drawing, I see the total height, and I see the width and the depth. So it's a 1 inch by 1 inch by 1.875 inch object. So I can add those. And at this point, I'd recommend just pulling up the drawing on your own. Try to work at your own pace if you can. If you just want to follow along, that's also fine. If you want to like get a walkthrough of how to read these drawings. but there's my first sketch. I'll extrude that since I'm trying to make a 3D object here. And the depth is 1 inch. And the reason I know that is because here it's 1 inch by 1 inch. So this is the beginnings of my cylinder. We have our rectangular prism. So from here, what's the next feature? I think one of the most important features in this object is this big cylindrical hole. And in the past, we've done these kinds of holes before. We create a circle and then we extrude cut. And that is one way to do this, but I think today I will introduce a bit of a different tool that you can use to create these kinds of holes. So what we're going to do, I want the hole to kind of go down, like drilling into this top face. So I'll create a sketch on this top face, and you can do that just by clicking the sketch tool and then clicking on the thing you want to sketch on, which is that top face for me. You can see where my sketch plane is, and that looks right to me. So I'll look at this, and instead of creating a circle, instead of sketching the circle, what I'm going to do is just sketch the point where the center is going to be. So if you recall, we have a point tool, which lets you create a point just like that. And now I need to locate this point. And the location of this point is pretty much determined by these dimensions here. So you can see from one end, it's 1/2 inch from the edge. From the other end, it's 3/8 or 0.375 inches away from the edge. So in terms of position, those two coordinates, those two lengths are all I need to know. So I'll go ahead and dimension it. To dimension the location of a point, you can just click on the point, click on the edge you want to distance it from, and type in a number just like that. So one more time, you click on a point, you click on the edge, and you can just type in a number. So there you go. Those are the only two numbers we need. And you can see the point turned black, and point is the only thing in our sketch right now. So I'll give you a second to get to this point. Pun not intended. Let me know if you have any problems here, but I'm going to introduce now a new tool that you can use that'll make life a bit easier when it comes to making holes. All right, so no questions. I'll show you the great tool. It is called the hole tool. And as you can imagine, it creates holes. So you might be asking, why would they make this tool when we already have the extrude, which can remove material? That is a good question, and it kind of ties back to what I was talking about with the McMaster stuff, where a lot of the times you're going to be designing components or assemblies to use standard hardware. And so whether you buy this product in one part of the country or another, you want every piece of standard hardware to work with whatever you design. And that's why the size of your holes actually is very important, because if you make the hole diameter just based on whatever you feel like, there's a good chance that it won't fit with any of the standard hardware that exists. So the hole tool saves you a bit of trouble by, you can see if you click the hole tool, just like any other tool, it brings up this window, and you can see it basically tells you all the dimensions that you need in order to have a standard hole that will fit the standard hardware like bolts or screws. So there's a lot going on here, but don't be intimidated. Most of it you don't really need to deal with unless you're designing something important, I guess. All you need is a very simple hole. So I'll go with simple for the first option. For the second option, we have these three words, which you've seen before when it comes to extrusions. So through means that it goes all the way through. That's what a through hole is. And then don't worry about these, but just know the blind means that it's not through. So it stops somewhere in the middle of the solid. So it's not a through hole. It's kind of, it just goes in and there's more material in the back. So I want a blind hole since this is not a through hole. The hole doesn't go all the way through the block. It's blind because it stops before it goes through. So we have simple, we have blind, and then we have this weird thing called standard. And so when it comes to standards, in America, we have this thing called ANSI. It's the American Standard Association or something. I don't know what it stands for off the top of my head. There's also ISO. And those are the two big ones. When in doubt, just leave it on ANSI. And for the most part, if you ever need to actually create standard holes, they'll probably tell you what to use. Likewise, so in this case, actually, I'm going to tell you what to use, which is custom. So this isn't actually, this hole, this long cylindrical hole isn't actually meant to fit a standard piece of hardware. Rather, it's, as you can tell from the name, this thing is supposed to be a cylinder, which means that there's a piston that's going to go inside. So the thing that's supposed to fit inside this hole is a thing that we're also making, which is why it's a custom hole. So just set it to custom, and that gets rid of some of the options. Now you can tell what's happening here based on these little icons on the left. This first icon is kind of the diameter of the hole. So if you look at the image here, the fact that there are two numbers here just means it's trying to tell you what the tolerance is. So don't worry too much about that, just pick one of them. I'm going to pick 0.5 because it's easier. So I'll type in 0.5. And the other parameter that you need for a hole is its depth. So look on the drawing, I'm looking, and I see here, this is the depth of the hole, 1.625. And you can tell just because it starts from the bottom and it goes to kind of where this hole stops. I forgot the number already, 1.625, 1.625. So that much is done. And for the last thing, all you need to do is tell Onshape where to put this hole. So for this field, where this box is, sketch points to place holes. Well, we just made the sketch point, right? That's the sketch point, and if you click on it, it'll create the hole for you. And it's pretty much all you have to do. You can see in the preview that the tip of the hole has kind of this cone shape, and that's kind of what was going on over here. You can see there's a little triangle in the drawing. That means the hole terminates in a cone, and you can see in the model preview that the hole terminates in a cone. So it's very convenient. Do you have a question, Jason?
How to make a sketch point again?
Yeah. Let me just go back to that sketch. So in terms of points, I think we've used the point tool before. It's the one, I guess, to the right of the spline tool, to the left of the letter tool, kind of the sixth one in your sketch tool section. It just looks like a dot. And the way you use it, you click the tool to activate it, and you just click anywhere in your sketch, and it'll start placing points wherever you click, like so. And so what we did before was just creating that sketch point and then dimensioning it. And hopefully that's straightforward enough. To dimension it, what you do is you get your dimension tool, you click on the point, and then you click on an edge, and it'll just pull up that dimension. So nothing too complicated, just it's a matter of knowing this new tool that we just learned, which hopefully is clear. And from there, you're able to set up this hole just like that. So I'll leave this up for a second. If you have any questions about the hole tool, please ask. All right, if there are no questions, then accept your hole. The model is one step closer to being done, but there are still these 2 holes that we have left to do. And the way that we're going to approach this is exactly the same. We're going to make another sketch. We're going to place 2 points in that sketch, and then we're going to use the hole tool to make those holes. So let's get right on it. First of all, we need to kind of figure out where we're going to make this sketch, because at this point, our part is no longer symmetric. Before we had kind of this square prism where it didn't really matter what we were doing, but now, since this hole is not centered, we kind of have a bit of a choice to make. Like, not all 4 of these faces are equivalent anymore. They're all different, as a matter of fact. So we need to look very carefully at our drawing. So we look at the drawing, and when we look at the side view, this is the most useful one. We can see that the holes come in from the side where there's a lot of material between the edge and this big hole. So what we're probably going to want is this edge right here, as opposed to, say, this edge. So take a moment, identify which face that you're going to be sketching on. For me, it's this one. I'm looking for the one that's far away from this hole. And conveniently for me, it happens to be on the right plane, so I can just create a sketch on the right plane. If it weren't, I could still just click on this face and it'd be fine. So go ahead and create a sketch on that plane, on that face that you identified. And once you have, we're going to do the same thing, right? We're going to place 2 dots. We're going to fully constrain those dots, and we're going to finish the sketch. So let's get started. I know I need 2 dots, so I use the point tool, and I just put 2 dots anywhere. Doesn't have to be anywhere close to where they're actually going to end up. Now, where do these go is the next question. So if we take a careful look at the drawing, first we need to orient ourselves a bit. Which way does the hole open? So is the opening of the hole in the bottom or the top of this block? So hopefully you can see that with the way that this sketch is drawn, that the opening of the hole that we made is at the bottom of the block. You can see here, the triangle here is kind of that pointy end of the hole that we made. So all our measurements are being taken from the opening, the mouth of the hole. So this is that face. You can see here, there's nothing here. So we're making our measurements from this being the bottom. So that's good to know. I'd recommend getting your bearings. Now, with that, I can add some of my dimensions. So where's this bottom hole located? It's located 0.875 from the bottom. So again, like we did with the other one, you can just create a dimension, give it a number. That's 0.875. What's the other one? I look back at the drawing and it's 1.5. So from here to here, just sketch 1.5. So that's half the work done. Now we just need to finish constraining these points, which are still free to move left and right. There's a bunch of ways that we can do this. I could maybe take this midpoint and just make all 3 of these vertical. I could create a construction line that goes up and down here and make the points be on that construction line. I have some options here, and I'm sure you have the options as well. So if you feel confident, just do whatever option you need to make sure these points lie kind of on this midpoint. The one I'm going to choose is just to use this vertical constraint. just so I don't have to create any more sketch things. Since Onshape actually just lets me hover over the midpoint here, I can click the midpoint and I can click the point all with my vertical constraint tool. At least I thought I could do that, but maybe I can't. In that case, for starters, I'll just make these two vertical with each other. So that's my first constraint. Now you can see that they move together. And for my second constraint, let me just try this one more time. I guess I can't. So in that case, maybe I'll just add a dimension. So from here to here. Since I have a bit of information about this whole thing, I know that this is 1 inch long here. And I see this midpoint line, this blue line, that's a mirror line, essentially, or symmetry line. That tells me that the holes are in the middle. So I know that the middle of 1 inch is ½ an inch. So I just type that in for convenience. Of course, from a design perspective, you probably just want to use constraints and construction lines because those will properly update if you ever change the geometry. But I know we're not going to change the geometry, so that's what I did. So you want to have something like this, and from here we're almost done. Let me know if you have any questions with this one, but hopefully it's the same thing that we just did before with an extra hole. Nothing too crazy. So last step is to use the hole tool. We're going to use this twice because the two holes are not the same. Let's start out with this hole, which has this weird label on it. It says 1032 thread 0.25 deep. And that might not make a whole lot of sense to you, and don't worry if it doesn't. The only thing that we really care from that message is the 1032 part. So let's identify which of these two holes that is. Just by looking at this, the one that we're trying to do is the one that's closer to the opening. So closer to the opening, that's this one. So I'll just click on this one for the moment. Now, we still want a simple hole. We don't need anything fancy. And it's still a blind hole because it's not going through. But this time, instead of a custom setting, we're going to use the ANSI standard. That's the one I told you is kind of the default American one, I suppose. And from here, these settings matter if you're going to actually manufacture this thing, but in our case, it doesn't really matter. Properly, we should, I think since it's taking a thread, we should be using tapped, but it doesn't matter too much. Set it to tapped for now because that's technically the correct one, but if you're ever trying to do this on your own, really just don't worry about it. Now this is where the 1032 part comes in. 1032 is kind of the way the standard works. So the size is a number 10. And the threads per inch is a 32. So 1032, this thing on the drawing is just kind of telling you what numbers to pick in the hole tool, right? Engagement, don't worry about that unless you're manufacturing. If you're curious, if this is going to be made out of aluminum, you'd pick 75%. And you don't have to touch any of these. These are now the correct numbers. You didn't have to look up any tables. You didn't have to do any calculations. It just gives you these numbers, which are going to be correct based on what you picked in these dropdowns. So that's pretty good. And as a matter of fact, we are done. I will also, one thing, the depth of this hole is 0.25. So for me, by default, this was 0.25, but this is the number you should change. Like I could put 0.2 there. I want to put 0.25 there, but this is the one number you have to change. This one you don't change. These, I guess you can change, but don't change them, or don't feel the need to change them. And that's all you need to do, and that's that hole finished. And so we're almost there, just one more hole left. And this one is interesting because it actually joins up with the big hole. So when we drill this hole, we're actually going to be able to see through this part. So what information do we have? All we know is that it's 0.125 or 1/8 of an inch in diameter, and that it goes all the way through to this hole. So it's not a through hole, but it ends up joining with that whole other hole. So we're going to use the hole tool again, but we need to make sure we can see that sketch where we drew those 2 points. So you might have to go into your feature tree and click the eyeball. That'll make the points visible again. From here, you can use the hole tool. Same tool as we just used. This time you click on the other point that we didn't use yet. And again, now it's still a simple hole. It's still a blind hole. Now it's a custom again. The diameter is 0.125. And as for the depth, the drawing does not specify a specific depth, but we know that we need to go deep enough that we'll be merged with this big hole. And so just based on what I know about this part, I know if I go, for example, 0.5 inches, that's enough to go all the way through. So for the depth, I'm just going to put 0.5. And if you look closely here, you can see now in the preview, the hole kind of pokes through. You can see it from the inside of the big hole, and it doesn't go so deep that it goes out the other end on this side of the wall. So the main thing we learned from cutting this part is how to use the hole tool, how to create sketch points, and more experience in reading drawings together. So you can see this part is completed now. We have all the features that exist in this drawing. And so this is our finished model. So hold on to this, keep it in the same document where you made your base plate for the homework. And I think 2 weeks from now, we'll end up assembling the steam engine. So get excited for that. My goal was to go through this crank wheel as well, but that may have been a bit ambitious. You can see, looking at this drawing, we have kind of a cylinder with another cylinder on it. So kind of 2 cylinders on top of each other, one's bigger than the other. And there are 2 holes in here. So in theory, now you have all the tools that you need to know to create this part. One part that could be tricky is trying to create a hole on this curved surface here. What you can do is you can just sketch it on this vertical plane, the one that goes this way. If you create the sketch on that plane, you should just be able to create a hole. But we're not gonna have time to go through that today because I believe we started at 4:30, I believe. So we should be wrapping up in a moment. So in terms of the homework, so last week the homework was to model the base plate, which you did attempt, and hopefully some of you have finished. I'd say for the next week, focus on trying to model this part. So it's called a piston in that big here in this Google Classroom. If you go through the drawings, look for the one that looks like this. It'll be called piston. And this part is fairly straightforward. It's just an exercise in knowing how to read the drawings, knowing what shapes are present, knowing how to find your dimensions. And this time there's kind of a new thing, which is using the hole tool, which is the main point of this lesson this week. One thing I'll say before before you run into this and don't know what to do, there is going to be some cases where there are two numbers listed for dimension. Like for here, you can see there's 0.142 and 0.144. In this case, this is trying to represent a tolerance, which is just telling the person who's making this thing how inaccurate they're allowed to be. But when it comes to making the model, we don't have to worry about that. So when you're using Onshape, just pick one of these numbers and use that as the diameter. Don't worry about the tolerance, just put in any number that you think is good. So you can just put in 0.142. For this one, you can just put in honestly, you can just put in 0.5 for that. It's actually 0.4997, but for our purposes, that's basically 0.5. So there's that. If you have any questions about the homework, your priority should just be try to model this piston. And if you want to do more, of course, finish your base plate. And for a challenge, try doing the crank wheel. Next week, I think I'll either go through the crank wheel together with you or go through a different part to teach you a different skill. But in a couple of weeks, we'll have all the parts modeled and we'll be able to assemble this thing. Here's that picture of it. So for this class, that's all we've got. If you have any questions, if there's anything you need, feel free to ask, but we're done for the day, I believe.